great to be here, seeing this community grow over from last year to this year. So it's great to be here again. My name, as Zach said, is Alex. I co-founded Logsight approximately 3 years ago. And I thought a lot about what we are actually doing at Logsight. And the thing is, in my opinion, it's something like helping companies to keep up with the rapid pace of the tech world, right? Because tech itself is really fast progressing, but if we take a look at the previous years around AI, then it's an insane speed at which technology is published out there. So it gets more and more difficult for companies to keep up with it and also participate in this technology. And one specific project that we are currently working on is we are trying to optimize the operation of large language models. However, since we worked in this topic for a few months already, we see that this technology is not specific to large language models, but can be applied more generally to other models as well, like image models and voice models. And what we are trying to do, as I said, is to balance cost, efficiency, and sustainability there. So let's start. I think most of you heard this question more or less already. How much of AI is real? How much of it is hype? Is there a bubble around it? Obviously, I don't know. What I know is that a lot of investors at big tech companies are putting a huge bet on this technology, right? This is what we can see. And the other point is also that there are a few companies at the moment providing compute which earn a lot of money due to the way AI is developed today. And the other thing that we can observe is that AI seems to be useful, although in a quite early stage in the products at the moment, they seem to be quite useful for a lot of people. Here you can see a study, for example, done by the University of Chicago. They surveyed 100,000 people and asked them whether they are using ChatGPT regularly on a weekly basis, either at work or privately. And the overall result here is obviously the tech people are using it more than non-tech people, but still, even non-tech professionals seem to find this technology useful and they're regularly using it. So let's step back one moment and take a look how we got here. I think all of you know that AI has a very rich history dating back almost 100 years. However, unfortunately, I don't have time to cover all of it today, but I will try to pinpoint here two key technologies that were invented that basically allowed or enabled the training and development of AI models at scale, which are actually powering the products that all of us know today. And this was AlexNet for images and the transformer model for natural language processing. Before that, before these technologies were published, you could say that the model architecture itself was the main bottleneck for AI progress. It simply wasn't possible to train arbitrary large models on huge clusters due to technical difficulties like the gradient vanishing problem or due to the inability of training recurrent neural networks in parallel on huge clusters. But after the invention of these technologies, it became possible. However, it took another 3 to 5 years to figure out how the scaling laws of AI are actually working. Although they are quite simple, basically stating that you can throw a huge amount of data on huge models and something amazing will happen, it still took some time for people to figure it out. However, after figuring out and getting access to enough GPU hardware, we see that these amazing products were published there, DALL-E and ChatGPT, and they broke a lot of records regarding user adaption. And after seeing this traction, big tech companies basically got aware of this technology and joined the competition to build the biggest and the best models out there. And they bought a lot of GPUs, basically ramping up this curve to GPU investment by a lot. Now, what's possible when buying such amount of GPUs? It's possible, obviously, to train in increasingly large models. Here we can see a study which analyzed frontier models at the moment across different companies, and they say that or they conclude that AI models at the moment are growing by a factor of 2 every 6 months, approximately. What is the cost of training such models? Here I brought some numbers regarding the GPT models that were reported by OpenAI. You can see that the GPT-3 model took 34 days to train. GPT-4 model took 100 days to train. I mean, that's a factor of approximately 3, which is still fine, I would say. However, it took 50 times more energy to train GPT-4 compared to GPT-3, which is a quite huge factor considering that these two models were released, or the release of these two models is only 2.5 years apart, approximately. So this is only for the training, right? So what happens if we train the models? We need to deploy them on our infrastructure, and we need to run them in order for them to be able to serve the prompts of our users. And here I brought a few numbers that you can compare them. On the left-hand side, it's still the training numbers of GPT-4. On the right-hand side, you can see the inference numbers, also for the model GPT-4. GPT-4 is reported to answer approximately 3 billion prompts per week, which sums up to 156 prompts per year. And it takes 454 gigawatt hours of energy to actually answer this amount of prompts for GPT-4. It's basically, to put it a little bit into context, it's basically the same amount of energy that is needed in order to power the city of Potsdam for a whole month, which is quite a lot, I would say. So just to summarize until now, initially we had the model architecture itself as the bottleneck, right, for AI. It was solved by the invention of the technologies that were published by researchers. The next bottleneck was the availability of compute hardware, which was quickly solved by NVIDIA, bringing a lot of GPUs on the market, enabling companies to buy them. And now we are approaching the next bottleneck, which might be energy. So at some point in future, it might be the case that we will have more compute hardware in our data centers than we could actually, than we are able to power, actually. For me and other people working in this field, it looks a little bit like we are brute forcing our way into AI innovations by doing that. Because you could ask yourself if it's really necessary for an AI model to be able to write poetry, know the whole history of the Roman Empire by heart, encoded in the weights of the model, and do arbitrary translations between different languages. Because by building this one mighty AI model that can do basically everything, we are running into several problems, which I would like to highlight here. The first one is the accessibility of this technology. Because only big tech companies are able to build models at this scale, individual researchers, universities, research institutes, smaller companies are all left behind and cannot participate in this development of this technology, which is a quite bad thing in my opinion. The second part is the limitation regarding the use cases. Whenever you need models to answer very quickly, whenever you need to process a lot of data, whenever you need to run your models in environments where compute is limited, you're not able to do it with these large models. And the third part, obviously, is the environmental impact. It is reported that AI will require 136 terawatt hours of energy by 2027, which translates to 500 megatons of carbon emission, which is simply too much. So we as engineers, I think, have the responsibility to think about how we can approach this problem and how we can do better. And there are 3 areas where we can actually improve from a technical perspective. First of all, it's the model. We know that the model size is the major driver of inefficiency, so we can try to reduce the model size and while trying to keep the model quality as high as possible. The second part is the fact that there are a lot of GPUs already deployed in our data centers. So we need to make the best out of this resource. So basically to utilize the available resources as efficiently as possible. And the last part is the infrastructure. Whenever we deploy large language models, we need to make sure that the infrastructure of our data centers and the technology that's basically serving them is designed in a way that allows an efficient operation of these models. And now in the next few slides, I would like to dive a little bit deeper into each of these segments and to discuss possible approaches there. So let's start with the model optimization and the objectives there. For model optimization, we try to reduce the memory footprint, basically the amount of memory that the model requires on certain hardware device, to a minimum, in order to be able to serve more models on the same amount of hardware, or to serve models on hardware that is not that performant. And the second part is to reduce the compute runtime, because then we can basically process more data in less time and increase the efficiency of our workload. And this would obviously increase the accessibility of this technology, the use cases that we can cover, and also the environmental impact will be reduced. So instead of giving an overview of all the model optimization techniques that are out there, I decided to dive a little bit deeper into one specific technology, which is called weight quantization. And I would try to briefly explain this technology because it's, from our perspective, it's quite capable, and it allows to run AI models more efficiently without too much cost associated with it. So you don't need to do a lot to achieve this. So weight quantization basically transforms the representation of each model weight that you have in your AI model from one data type to another data type. So usually the weights of a model during training are stored in floating point 32, which requires 32 bits to store 32 bits of storage for each weight in your model. And by transforming this data type from FP32 to int8, you reduce the amount of bits that are required to encode the weights from 32 bits to 8 bits. What you can achieve with this is you can reduce, obviously, the amount of memory that is required to load the model into your, on your devices to a third. And you can also increase a little bit on the runtime. However, you might think that when reducing the resolution of the weight encoding, probably some of you are familiar with Shannon and information theory, you're basically reducing the space that you have available to encode the information inside your model. And the assumption here is that the model might, or during model training, the available weights might not make use of all the space available to them, the 32-bit space. Actually, there are less information, but encoded in a very sparse environment or sparse space. And by doing a kind of adaptive transformation from one encoding space to another encoding space, we try to not cut away information, but encode it into a compressed format. So we can basically encode the same amount of information in a smaller encoding space, which translates a little bit to the compression of the model and not the reduction of information there. And actual publications, this is one, but there are many out there that actually confirm this. They show that you can do this transformation with losing only a tiny fraction of model quality. There are other model optimization methods out there, for example, pruning and distillation, where you actually reduce the size of the model and cut away some weights. You're doing it in an iterative way of cutting away weights, then doing a little bit of fine-tuning to improve the quality again, and do this several times. And researchers from NVIDIA showed that you can cut actually the size of the model by 50% and not lose too much information. The other possibility is a mixture of experts, where during runtime you only activate a subset of the available weights in the model, which significantly improves the runtime of the model. However, the runtime improvement is hard to estimate because it really depends on the architecture that you use with your mixture of experts approach. So what can we gain with the model optimization? We can save up to 80% of memory and save up to 60% of compute while maintaining a very competitive model quality. So you almost get these kind of numbers for free if you do it correctly, which is amazing in my opinion regarding the model optimization. The next part that I would like to cover here is the system optimization. So with system optimization, we would like to optimize the way we calculate the workload of our model on the available GPUs, right? And before doing that, we need to actually take a look at what kind of computations are executed on our GPUs while computing an output in our models. And it is basically a set, or mainly matrix multiplications and addition operations. This in parallel system programming, this is referred to as embarrassingly parallel workload, which is an official term, by the way. And it basically states that you are able to split this operation into many, many sub-operations, running them in parallel and combine them at the end without an increase of overhead. So now we have a workload that can be parallelized, right? Now we need to think about how to execute this workload on our available hardware. And GPUs are really, really complex stuff. Here, for example, there are a few numbers regarding the A100 GPU from NVIDIA, which consists of 108 stream multiprocessor units. Each streaming multiprocessor unit have 128 CUDA cores, four tensor cores, and 1 RAID core, which sums up to an overall more than 14,000 cores that can be used at each cycle to compute workload in parallel. This is a quite complicated thing. And in order to measure the utilization of our GPU, we need some kind of a model. And what we are using there is a so-called roofline model, which you can see on the left-hand side, where we measure the arithmetic intensity. This is basically the amount of operations that were executed on the bytes that we loaded into the memory. And we compare it to the actual amount of available performance, which means the overall performance of our GPU and how many operations it can execute per second. And the task of optimizing our AI workload on the GPUs is called kernel optimization, and it really makes a difference. So when you, for example, optimize a certain kernel that can execute the workload of a specific model on a specific hardware, you are able to gain performance increase by 1.3x for smaller models and 5x for larger models, which is a lot. So basically, you're not changing the model architecture at all, but you're optimizing the way the workload is executed on your hardware devices. And with this, you can basically save up to 70% of compute on by optimizing the kernels, basically the workload that is executed on your GPUs. I would really love to dive into the infrastructure optimization topic, but unfortunately, I think I'm running out of time, so I will skip this one, and maybe we can discuss it afterwards during a coffee break. Therefore, I would like to summarize and conclude this talk. So, what we can see here at the moment is a little bit of a counter trend to this kind of model scaling in the open source community. So really smart people, fortunately, are thinking about how we can provide alternatives to this kind of a brute forcing approach in AI. And I think our responsibility as engineers is to keep track of this progress and these technologies and to apply them in our use cases, in our daily work when we develop AI as best as we can. And I believe that this will basically increase the accessibility of these technologies, so more researchers will be able to participate in the development of AI. It will increase the amount of use cases that we can cover with AI models, and we can do it in a way that is more responsible, where we reduce the impact on the environment as much as we can. Thank you very much.
Thanks a lot, Alex. Do we have questions? I certainly don't have a question because that's beyond where I can improvise. I'm very happy. Please save me. Yes, yeah. We have the microphone en route. Two over there.
So,
Yeah.
yeah, quick question. As you pointed out, quantization is doing wonders. You see Thomas Wall from Hugging Face saying we are running very cool models now on computers, very cool stuff. However, be it as it may, you still need sort of specialized workforce to set these in place, and then you need to know which model is performing better at which task, which again means that companies might prefer the large model that you can call with an API instead of hiring a bunch of developers for this. So how do you see this evolving in the future? This was one question, and then a quick side question. Why don't we train directly on int 8 instead of floating point 32, instead of doing it after the training? Thank you.
Yeah, very good questions. Thank you. So first of all, the first question is basically, how do I see the development around these small models? I think that there will be use cases where companies might prefer to work with large models now, but I think the future looks a little bit different. I think in future we might work with an API, with a set of APIs where you can basically access models that are specialized on certain tasks, right? So they are much smaller. And therefore, the computation of each of the prompts that you send to them and the reply that you get will be much faster and energy efficient. And I think, of course, in my opinion, you will still end up with this kind of huge data centers that are operating models. We just need to think about what kind of models we put there, right? Either it will be one model covering basically all of our infrastructure, or it will be a set of specialized models that allow us to serve more requests in less time and therefore make the best out of this available compute technology already out there. So I think it will be more regarding like agents and specialized models for certain tasks.
I think there were two more questions, right?
Yeah, thank you for this great presentation. So if I understood this correctly, most of what you said applies pretty much to inference. And I was wondering, if you democratize inference, that's great, but we're not democratizing building the big models in the first place. So I was wondering, does any of this also translate to building a new model from scratch, making this available to, let's say, smaller entities or researchers?
Yeah, very good question. I think we thought about this a lot, like really a lot. What to focus on, right? Either inference or training. I mean, the way we are currently understanding it, but it might be obviously wrong, but the way we understand it is when you develop an AI model, it is something like an investment that you do, right? So you're basically investing into like a machine that will in the end be deployed and it will serve the need of your users. And to making a one-time investment, which is plannable, to build this one model that is useful to you, this is a process that we think is still fine, and it is tolerable, right? But after you develop this model, you need to think about how to run it over several years in an efficient way, right? And we think this problem is, at the moment at least, more important to solve compared to the training part. Therefore, we are focusing on inference.
One quick question left. And before we move on, I remember, I think, now you ask a clever question, but last year you actually explained inference, right? You had that keynote? Yes, so that's a good moment to point out that all of these talks will, of course, be available for you guys. If you enter the Deconium platform, you can watch all of these talks, and there are some brilliant talks already from last year, for example, about inference. So if you want to connect those two conferences, that's the way to go. Perfect. There was one quick question.
Hi, thank you. Thank you for this interesting talk. I was just wondering, have you looked into these new kind of architectures where you don't have weights at all? And would really like to know what your opinion about those are and if those could be a game changer or not.
Yeah, very good question. We looked into these architectures, yes, but I think from our experiments, they're quite in early stage yet, right? So it's very, like, a lot of it is more or less fundamental research at the moment. I personally think that it's really important and great that we are working on alternatives to this approaches that we have at the moment. But of course, from an project-based and business-based approach, these technologies are still too early in order to be applied to real customers. So we are taking a role of observers to this technology, and we are trying to apply the things that are already out there and deployed to customers in order to optimize them first.